Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to week 4. Now, the last few weeks now, we have been talking about this bottom-up view to transport, to the flow of current. And this week, we'll use this viewpoint to talk about a whole new class of devices and effects. You see, a field in which there's been a lot of important developments in the last 20 years. It involves manipulating what we call the spin of the electron rather than its charge. And what has happened in the last few years, actually, is that two fields of research that used to be completely distinct, namely spintronics and magnetics, they have all kind of merged into one big field. And what I'll try to do this week is give you a feeling for the developments in the field and how we think about these things. Okay? So let's start with the basic structure that we have been talking about, again, much of this course. Namely, you have a channel with two contacts, which you call the source and the drain. Now, the only difference now is that we'll consider a magnetic contact. So far you see the contacts have been just ordinary materials. But suppose we have these two magnets, the two contacts are two magnets, which say point upwards. That's the magnetization. They're all pointing in this direction, let's say. And let's start then by discussing one basic experimental fact that was first demonstrated now a little over 20 years ago, and which quickly found a lot of important applications. See? And it was recognized with the Nobel Prize a few years back, I believe in 2007. And the basic effect is the following, that if you have these two magnets pointing in the same direction, parallel, then let us say we measure the resistance. As we discussed, resistance is, voltage divided by current. So when you put a voltage, a current flows, and the ratio is this resistance. And this resistance with magnets parallel, let me call that R sub P. Write it a little bigger. Now, you could also measure the resistance with the magnet's anti-parallel. That is when you switch the magnet to point in the other direction. So supposing instead of having it point upwards, let's say we make it point downwards. Now, and the corresponding resistance that you measure, let's call that RAP. So that's the anti-parallel resistance. And the basic experimental fact is that the parallel resistance is less than the anti-parallel resistance. So this is less. Now, why is that useful? Well, you see, in hard disks, the way you store information is in the magnetization of magnets. So, for example, if you had a magnet like this, this could be a bit of information on your hard disk, and depending on whether it is upwards or downwards, it represents a 0 or a 1. And what you need is some way of measuring it, figuring out whether it's a 0 or a 1. Now, the thing is that this effect allows you to do that, because what you could do is come in with another magnet that points in a certain direction, and if it happens to be in the same direction as the stored information, you'll get a lower resistance, because that would be the parallel resistance, than if this was in the opposite direction. So by making use of this effect, by measuring that resistance, you can essentially tell what the information stored is. You see, and this is one application this effect found. It was being used for, it was probably in the 90s that this application developed, people figured out how to use this effectively to read information. Okay. Now the question is, how do we understand this? Now this is where what I'll describe to you next is a model that helps you understand why the parallel resistance should be less than the anti-parallel resistance. And the argument goes something like this. I've earlier said that when you look at this channel, usually the states that are available in this channel for electrons to flow, for electrons to conduct, they always come in pairs. There's an upspin channel and then there's a downspin channel. And usually we haven't talked much about it. We say, well, there's an upspin and a downspin, so whatever we get, we need to multiply it by the degeneracy factor, G, which due to spins would be 2, and you'd multiply it by 2. So the quantum of conductance, let's say, is Q square over H. But if someone actually measured the conductance of a narrow wire, they would normally get 2Q square over H. Why? Well, because there's 2 spins. That's what we've been saying. Now, this week though, we need to take those 2 spins explicitly into account. We'll be talking about phenomena where you just can't multiply by 2. So the idea is, well, here's this channel. So mentally you can think of it as if, the channel has these 2 parts to it. One part is the upspin channel, and then there is another part which is the downspin channel. There's 2 of them. So, and these electrons, the upspin ones can flow there, and the downspin ones can flow there. Sort of like 2 separate lanes on your highway, if you will. Okay. Now, we can understand this basic experimental observation if we postulate, and at this time, let's say we're just postulating it. A little later in this week, I think it would be the 4th module or so, where I'll try to explain a little better why this postulate, how to understand this. But the postulate is that when you have a magnet pointing upwards, it has a relatively low resistance contact to this channel. What it means is I'm trying to model this as some kind of a resistance here at this interface between the contact and the channel, and again some kind of a resistance here, and then there is some resistance in between. One of the things we have talked about earlier in this course is how there is a resistance in the channel, and then there is the interface resistance associated with the interfaces. So we have something in the middle. So we'll call this, say, R channel. And then you have got these 2 resistances at the 2 ends. And for the blue channel, you have a similar story. Now the point is that what we are postulating then is that when you have a magnet that's in the same direction as the spin, then this tends to be a low resistance. So to indicate that it's low, what I'm going to do is put a small r. That indicates it's low. And similarly, if that's also a magnet pointing upwards, you also have a low resistance on this side. So I'll put a small r there. Now by contrast, when you look at the blue channel of course involves spin pointing downwards, and that's in the opposite direction to that of the magnet. And so it has a big resistance, and I'll denote that with a big R. And the same on the other side, so it's a big R. Now as far as the channel goes, it's basically the same resistance, because as we have discussed earlier, this channel is no different from what we have been talking about for the rest of the course till now. They are just ordinary non-magnetic material, and we know there's just 2 channels which are essentially identical. So those resistances are basically the same. But what you might ask is, well, why should a magnet have a low resistance to a spin in the same direction? What do spins have to do with magnets? Now, that's the part that at this moment I'm saying, let's take it as a postulate. A little later in this week, later this week, I'll try to explain that a little better, the connection between these 2 things. As I said, one of the important developments of the last 20 years has been this integration of these two totally, what used to be totally different fields, the spins and the magnets. Now, the question is, what is the resistance of something like this? You see, you're sort of, what you have is a little resistor network like so, and you're looking from here. And we're asking, what is the resistance of this? What is the effective resistance of a network like this? And for this discussion, let's assume that, let's ignore the channel resistance. Because, you see, the basic effect we are talking about, that comes from these interface resistances. And the channel resistance just makes the algebra a little longer. And, the effect is biggest when this is a relatively small thing. So for our discussion then, let's ignore this. That will keep the algebra simpler. Let's ignore that. So the question is, what is the resistance of something like this? And this you may remember from freshman physics, that what we have, let me draw that network up here again, so that we can work on this, and I'll leave out the channel part. So what we have is this R, and then another capital R, capital R. And what we are asking is, what is the effective resistance? And that is what we could call the parallel resistance, because we have assumed we have got the two magnets are parallel here. So the parallel resistance will be, so I've got this path with two resistors in series. So that is like 2R. And here we got again two resistors in series. That's another 2R. And the point is, those two are in parallel. Now, I don't know if you remember this law of how you add resistors in parallel. That's again something you see in freshman physics. You're supposed to add the conductances. So it's sort of like you take the inverse of this and the inverse of that, add them up, and then again take the inverse back. But the net result is that if you have these two things like this, the effective resistance is this times that divided by this plus that. This is the rule for adding parallel resistors. And so, if I write down the final result then, let me just write it here. It will be 2R divided by R plus R. All I did was cancelled out one of these 2's, and that's how you get that. So let me take this off. So that's our basic result. Good. So this is then the resistance of the parallel combination. As I said, the basic experimental fact is that this is less than that for the anti-parallel combination. So what does it look like for the anti-parallel configuration? Well, now what happens is, if you think about it, this second magnet is looking downwards. So now consider the red channel. So the red channel has a low resistance on the left-hand side because the magnet is in the same direction as the spin. On the other hand, when you go to the right-hand side, it has a high resistance because this has the opposite direction to that of the magnet. Remember, we are now talking of the anti-parallel configuration. So that one's pointing downwards. And so this is now in the opposite direction to that, and so you get a big resistance there. What that means is instead of small r, I should really put a capital R there. On the other hand, when I look at the blue channel, everything's reversed. It's like, this is, okay, I guess this still stays the same. I did not need to erase that. But this one is now the small r. Why? Because the blue channel now has a nice match there. It's in the same direction of the magnet, so it has a low resistance on that side. Well, so what's the effective resistance of that circuit? So if we get back to this picture then, it is like I now have R and a capital R, and this is big R and a small r. So now what you have is two channels, both of which effectively have the same resistance. One is small r plus capital R, the other is capital R plus small r. So the overall anti-parallel resistance then is equal to, you see, R plus R, that's the resistance of one channel, parallel with another one with an identical resistance. And when you have two identical resistors in parallel, the overall effective resistance is just half of that, because each one carries the same current, and so together they carry twice as much current, half as much resistance. So this one then, the correct answer is just half of this. That's it. Now what I can show, we'll do that in a minute, is that this will actually always be bigger than that. Now one limit where you can see it very easily is if the big R happens to be really large, let's say infinite. Let's say big R is very large compared to small r. You know, ideally that's what people would like to do. They would like to find magnet materials such that one type of spin has a extremely high resistance compared to the other. Now if it were really big, you can immediately see that the anti-parallel resistance would also be really big, because it doesn't matter how small this is. It's like a small thing plus a real big thing. On the other hand, when you look at the parallel one, what happens is you got a small thing plus a big thing, so you can drop the small thing, you have only the big thing, which cancels this. And so the parallel resistance is a relatively low one. And the physical reason you can see that, you see, if you look at this structure, if this happens to be a very big resistance, what it means is both channels have very big resistances, and neither can conduct very well. On the other hand, when we had the parallel configuration, if you remember, we had these two R's here and the two small r's up there. And then even if this is very large, that's fine. You still got one channel which can conduct easily. And so you get a relatively low resistance. Anyway, so the point is that when one R, this capital R is a big one, you can easily see why parallel is less than anti-parallel. But the point is this is more general. I mean, it doesn't have to be very big or anything. In any case, this will always be less than that. So let me show that quickly. The way it works is, actually people define something called a magnetoresistance. There is some difference in the way different people define it. The one I will be using here looks something like this. It's take the anti-parallel resistance minus the parallel resistance. They say this is bigger than that. So look at the difference and then divide it by the parallel resistance. So that's what you call the magnetoresistance, which is equal to, we just go through this algebra a little bit. So anti-parallel divided by parallel minus 1. So now the question is, what's this ratio? Let me take this off. So I can write anti-parallel divided by parallel is equal to, that's this thing divided by that thing. So what you get is, that's the anti-parallel, and then divided by this, so I turn it over and write it. That's it. And now I don't need this anymore, so I can take this off. What you can do is write this as And the denominator is 4 times the product of the two r's. And you can use a little algebra to write that in the following form, like plus r whole squared minus r. Yes. So this is this algebraic thing that a plus b whole square minus a minus b whole squared is 4 times ab. That's all I used here. Okay. So you can see that this ratio will always be bigger than 1 because you have something in the numerator and in the denominator you have the same thing. Take away a positive quantity. So the denominator is always less than the numerator. So this will always be bigger than 1. And of course, if the two r's happen to be equal, then it will just be 1. That's the usual case when you don't use a magnet. Then of course, parallel antiparallel is all much the same. That is, if both resistance are the same. Okay. Now you could write this also in a slightly different way, and that is, let's divide through by the numerator, in which case it will look like this. P square Now, this quantity here, this difference between the two resistors divided by the sum, that's what is often called the polarization of the magnet. It is a good measure of how effective this magnet is. See? So, let me just remind you. So, what we obtained is ratio of antiparallel to parallel. Let me take this off. So, I want to introduce this quantity here, P, which is defined as R minus R divided by R plus R. And that is a measure of how effective your magnet is and will appear in our discussion subsequently. That's P. And the basic experimental quantity you talk about is this magnetoresistance, which is what we just obtained, that is the ratio of the two resistors, which is 1 over 1 minus P square. And then I have to subtract 1 from it, minus 1. And that is equal to, you can show, P square divided by 1 minus P square. That's the other important result. And I should mention here then that what I just described to you is what applies to what are generally referred to as spin valves, where the channel is a conducting channel, like a metallic conductor. And recently what has happened in the last few years is a lot of the applications have shifted to what are called magnetic tunnel junctions. That is where the channel in between is a tunneling insulator. So the basic ideas are still similar, but in that case, the details of this is a little bit different. In fact, the correct answer when you go through it is not P squared divided by this, but rather there's an extra 2 there. And this I won't be going into. I just mention it here because a lot of the literature these days is about magnetic tunnel junctions, where the channel is an insulator. And so in the literature, you would often see that expression. What I do in homework 1 is I ask you to show, considering a tunneling insulator, why you would expect this relationship. And that's something I'll discuss in the tutorial when we talk about homework 1. So for this module then, these are the basic end results. The polarization and the idea of a magnetoresistance.